Hello there, and welcome to the Sleepy Space Channel. Tonight, a quietly unsettling thought experiment that has come to be called the Silurian hypothesis, the careful question of whether the Earth would preserve any trace of a civilization that had existed in its deep past. The answer is a sobering one. Civilizations, even global industrial ones, leave only the faintest geological fingerprints. The atmosphere relaxes back toward equilibrium within tens of thousands of years. The rocks hold a thin layer of altered chemistry, but the layer is subtle enough to be mistaken for an ordinary volcanic episode. Several brief, sharp episodes in the planet's deep past, in fact, resemble what an industrial civilization might leave behind. None of them is evidence of one. All of them have natural explanations. But the resemblance is unresolved, and the unresolved part is what we will sit with tonight. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is something you need to carry. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Part 1. The Scale of Deep Time. The question carries an unsettling weight at first hearing. We assume, without thinking very much about it, that we are the first. The first to chip stone into a tool. The first to plant a seed in a furrow. The first to build a city. The first to send a signal into the sky. The first to look up from this small green world and ask what else is out there. The assumption is so quiet and so constant that most of us never notice we are making it. And yet a small number of working scientists, looking carefully at the geological record of this planet, have asked the question in its strictest form. If a civilization had risen and fallen on Earth tens of millions of years before our own, would any trace of it remain? Would the planet itself remember? The answer, when honestly worked out, is the kind of answer that turns the original question inward and turns the listener slowly toward the long quiet of deep time itself. Before the question can be held properly, the listener has to be moved into the actual scale of Earth's past. Most people carry, without realizing it, a foreshortened sense of how long this planet has existed. Dinosaurs and the first human cities feel like they belong to the same long ago, vaguely sketched in the back of the mind. They do not. The distance between us and the last dinosaurs is so vast that almost no human intuition is calibrated to hold it without distortion. To approach the Silurian question with patience, we have to slow down and let the actual numbers settle. The Earth itself is roughly 4.5 billion years old. The Sun and the Earth condensed together out of the same slow turning of a vast cloud of gas and dust near a quiet edge of the galaxy, in a process that took only a few million years to set the planet on its course. Life, in some form, appears to have arisen within the first few 100 million years of the planet's existence. The earliest signatures are faint and chemical, hidden inside ancient rocks that have themselves been folded and reheated many times since they first formed. For most of the planet's long history, the only life there was on Earth was single-celled. Bacteria and other simple organisms drifted, divided, and remade the chemistry of the oceans and the atmosphere for roughly 3 billion years before anything visibly complex emerged. 3 billion years is a span so long that the entire history of plants and animals, of forests and fish and dinosaurs and people, is only a thin coat of paint laid over its end. Complex multicellular life arose only about 600 million years ago. The first soft-bodied animals, recorded as gentle impressions in fine-grained shallow sea sediments, were unlike anything alive now. Land plants and the first vertebrates climbed out of the water across the next 200 million years in the slow, halting move from sea to air. The dinosaurs ruled the Earth for 160 million years, a span that is itself difficult to hold in the mind. It is more than 2,000 times longer than the entire history of agricultural humanity. 66 million years ago, in a sudden global event, recorded by a thin layer of unusual sediment scattered across the world, the dinosaurs ended. A long age closed. A new one quietly began. After that boundary came the long stretch of the Cenozoic, the era of the mammals. The continents drifted slowly into their modern positions. Grasses spread across newly opened plains. Whales returned to the sea, abandoning the land that earlier mammals had only recently learned. Apes evolved in African forests. From one branch of those apes, some hundreds of thousands of years ago, the species that calls itself human emerged. Anatomically modern humans appear in the fossil record only in the last 300,000 years or so. Behaviorally modern humans, leaving cave paintings and complex tools and the first structured burials only in the last 100,000. Agriculture and the first permanent settlements only in the last 12,000. The industrial era, the era of machines and steam and electricity and globally manufactured change, only in the last 250 years or so. The contrast deserves a moment of stillness. The dinosaurs ruled this planet for a stretch of time more than 400,000 times longer than the entire industrial era has so far existed. If a technological civilization had risen and fallen at any point during their long reign, we would be looking back across a gap so enormous that the gap itself would explain the silence. The thumbnail of this video anchors the question at 69 million years ago. That date sits within the late Cretaceous, in the last 3 million years before the asteroid arrived. It is not chosen for any historical claim. It is chosen to illustrate the kind of temporal distance the Silurian question asks us to take seriously. 69 million years is more than 200 times longer than our entire species has existed, and more than 5,000 times longer than the whole history of agriculture. If something complex, something curious, something perhaps even tool-using and self-aware had existed on the late Cretaceous Earth, what would survive of it? What evidence would still be readable to us now? The honest answer turns out to be a quiet one, and an unsettling one if we are not patient with it. Almost nothing would survive. The Earth does not preserve the brief, sharp episodes of its own past with anything like the care our imaginations assume it does. That observation alone is enough to begin the inquiry. It is also enough to soften the question's sharper edge. The Silurian hypothesis, in its careful published form, is not a claim that anyone has been here before us. It is a question about the limits of geological evidence. It is a thought experiment about what kind of fingerprint a civilization would leave and how quickly the planet would erase it. The original authors of the published thought experiment have been clear, repeatedly, that they believe humans are the first technological species this planet has produced. The point of their inquiry was never to argue otherwise. The point was something quieter and ultimately more useful. They wanted to know, as astrobiologists, looking outward toward other planets around other stars, what an industrial civilization actually looks like in the geological record. They wanted a calibrated sense of what could be detected and what would be irrecoverable. And the only natural laboratory available for that question is this planet itself. So the inquiry begins here, in deep time. And at first, the deep time is the entire content of the inquiry. The listener has to be willing to set down, for a few hours, the foreshortened version of Earth's story that ordinary life requires us to carry. The planet is not a recent place. The planet is not a young place. It has been here for billions of years. Most of what has ever lived on it lived a very long time before us, in conditions almost entirely unlike the conditions we know, and most of what has lived on it has left no physical trace whatsoever. The fossil record we have is not a sample of life as it was. It is a sample of the lucky few organisms that died in the right place, at the right time, in the right kind of mud, and survived the long subsequent reworking of the planet's surface. The geological record is, at best, a fragmentary witness. To ask what it would remember of a civilization, we have to first understand what it remembers of anything at all. The patient outward survey that has shaped our knowledge of the cosmos, as covered in an earlier video on the listening itself, has produced only the natural universe in its findings. The patient inward survey that has shaped our knowledge of Earth has produced only ordinary geology, in patterns the planet's natural processes are sufficient to explain. The Silurian inquiry is not built on a discovery. It is built on the much quieter recognition that, if such a discovery had been possible, the deep record might not have preserved enough to make it. Tonight we walk slowly through that recognition, and we let it settle, and we let it open into the larger question it is really asking. A question about the long memory of any planet, and about what we may and may not learn when we begin to study the chemistry of skies that are not our own. Part 2. The Quiet Thought Experiment. The Silurian hypothesis, as it is actually written and discussed in the scientific literature, is a careful and deliberately modest piece of work. It is a thought experiment that asks one question and only one question, and it is patient enough to leave the larger speculations to others. The question is simply this: if a technological civilization had existed on Earth in the deep geological past, what would survive of it today, and could any of it be reliably distinguished from the natural processes that have shaped this planet? The name itself is a small piece of whimsy. It is borrowed from an old television serial in which a reptilian civilization was imagined to have lived deep beneath the Earth's surface long before humanity. The scientists who proposed the thought experiment chose the name partly to signal that they were not making any literal claim about a hidden civilization in Earth's past. The borrowed name is a kind of wink. The science the name decorates, however, is genuine, careful, and pointedly modest in its claims. The two scientists who published the original paper were a planetary scientist and an astrobiologist, working at the intersection of climate science and exoplanet research. Their motivation, as they describe it, came from an entirely outward-facing question. As humans begin to study the atmospheres of planets around other stars in serious detail, scientists need to know what an industrial civilization actually looks like, chemically and geologically, after its physical structures are gone. The published paper appeared in a peer-reviewed astrobiology journal. It was framed, throughout, as a calibration exercise. It was not framed as a historical investigation of Earth. The hypothesis is not a claim that a previous industrial civilization existed on Earth. The authors are emphatic on this point. They believe humans are the first technological species this planet has produced. Their hypothesis is a question about evidence. If a previous industrial civilization had existed tens of millions of years ago, would there be any way to know? What kind of geological signature would it have left? Could that signature be distinguished from natural processes? And, perhaps most quietly important, would the signal be more or less recoverable than the signal of any short geological event the Earth has produced on its own? The hypothesis is therefore best understood as detectability research, not lost civilization research. It belongs to a broader scientific tradition that asks what kind of signals would and would not survive across long stretches of geological time. The tradition is well established. Geologists have long thought carefully about what kinds of events leave reliable records in the rock, and what kinds of events vanish almost without trace. Atmospheric scientists have long thought about how quickly the chemistry of a planet's air relaxes back toward equilibrium after a brief disturbance. Astrobiologists, looking outward, have begun to think about how chemical fingerprints in distant atmospheres might persist or fade after the life that produced them has gone quiet. The Silurian thought experiment sits at the meeting point of these three traditions. It treats Earth's deep past as a laboratory for a question that astronomers will eventually have to answer about the deep pasts of other planets. The motivation also has a more reflective dimension. Asking what the Earth would remember of us 10 million years from now is also a way of asking what we are leaving behind, not as a moral judgment, simply as an observation. The Silurian thought experiment turns its question forward as much as it turns it backward. The same logic that asks whether a civilization could have been hidden in Earth's past also tells us, with surprising precision, what of our own civilization will and will not endure. The thought experiment is therefore a quietly humbling exercise. It calibrates not only the limits of geological evidence, but the limits of our own permanence in the planet's long story. There is a great deal of patience in the published version of the inquiry. The authors take their time to enumerate the kinds of signals that could persist. They take their time to enumerate the kinds of signals that would not. They are careful when they identify episodes in Earth's deep past that resemble what an industrial civilization might leave behind, to note that the resemblance is purely qualitative, that the actual fingerprints of an industrial source are absent from those episodes, and that the natural explanations of those episodes are fully sufficient. They do not argue that any particular event in Earth's past is suspicious. They argue, more carefully, that in principle, the record of an industrial civilization would look very much like a brief, unusual layer in the rock, and that brief, unusual layers are, by the nature of the record, very difficult to interpret with confidence in either direction. This carefulness matters. It is the part of the hypothesis that distinguishes it from the more excited cousin narratives that sometimes try to claim its name. The Silurian hypothesis, in its actual scientific form, is not a claim about Atlantis. It is not a claim about ancient astronauts. It is not a claim about any particular site, any particular monument, any particular extinction event. It is a calm, careful piece of detectability reasoning that turns out to have a surprisingly humbling answer. Yes, an industrial civilization in Earth's deep past would have left a faint chemical signature in the planet's sediments. No, almost any such signature would, after enough time, be very nearly indistinguishable from the natural background of the planet's normal activity. The Earth simply does not preserve brief, sharp episodes well enough to make the question answerable with confidence. To take this on board honestly, the listener has to be willing to hold two ideas at once. The first is that there is no evidence anywhere on Earth for any previous technological civilization. The chemical anomalies that exist in the deep record are all explained in the patterns of their full chemistry, by natural processes, by volcanic episodes, by the destabilization of methane reservoirs beneath the sea floor, by impact events, by the slow drift of continents into different orbital configurations. The second is that the absence of evidence is not, by itself, evidence of absence. The thought experiment's quiet finding is that even if such a civilization had existed, the geological record might not preserve the kind of evidence that would let us recognize it. Both things can be true at the same time. They are not in tension. They are, in fact, the two halves of a single observation about the limits of planetary memory. There is something gentle in this stance. The hypothesis does not insist on a hidden past. It does not invite us to look for buried temples or sealed chambers. It only invites us to think carefully about how long a planet's surface holds the record of its brief disturbances, and to notice that the answer for an industrial-scale disturbance is not very long at all on the planet's own timescale. The wonder it offers, in return, is the kind of wonder that only deep time can produce. We become small in this kind of inquiry. The planet becomes very old. The signals we leave on it, however vast they may feel from inside our own civilization, become very small and very brief and very quiet when seen across the long horizon of geological time. The Silurian thought experiment, read with patience, becomes a meditation on the patient memory of a world that does not particularly require us to be remembered. And yet, having said all of that, we still have to work out the actual mechanism. We still have to ask how the Earth's record is built and what kinds of things it can and cannot hold. Only then can we turn the question into a real inquiry rather than a posture. The next part of the evening is a slow walk through what the Earth actually remembers, and what it does not, and why. It is the most patient stretch of the inquiry and the foundation for everything that follows. From there, the question turns much sharper. From there, we can finally ask what a civilization would and would not leave behind in the long memory of a planet that was never really designed to remember anything in particular. Part 3. What the Earth remembers and what it does not. To understand what the Earth would remember of a civilization, the listener has to understand how the Earth's memory actually works. The planet is not a museum. It is a restless machine. Its surface is constantly being eroded, buried, melted, and recycled. Some parts of it are being lifted upward into mountains, while others are being scraped flat by ice. Continents drift across the face of the globe at the speed of a fingernail growing, and over many millions of years they crash into each other, lift up new mountain ranges, then erode those ranges back down to plains. The ocean floor is being pulled steadily into the mantle along long, deep trenches, and new ocean floor is being made along long, deep ridges. Nothing on the surface stays where it is. Nothing on the surface stays as it was. The Earth's memory of itself is the residue of all this restlessness, and it is much patchier than ordinary intuition tends to assume. Most of what we know about the deep past comes from sedimentary rocks. Sandstones and mudstones and limestones and shales. These rocks form layer by layer in places where particles can settle quietly out of the water or the air. River deltas, shallow seas, lake beds, ocean floors, dust basins in the lee of mountain ranges. Wherever there is a steady, gentle supply of fine particles and a place for them to accumulate without being immediately swept away, sediment can build up over time, and within that sediment, the record of the moment can be quietly preserved. Pollen grains, microfossils, the chemistry of the water and the air, the signature of life passing through. Sediment is deposited unevenly. A single year may leave only a millimeter of material in some places. A flood may leave a meter in a day in others. A long, arid stretch may leave nothing at all for centuries. The record is full of gaps, and the gaps are not always recognizable as gaps. Even where sediment has been laid down faithfully, only a small fraction of the deposited material survives long enough to become rock. Most of what is deposited is reworked by water or wind or ice, picked up and moved somewhere else, washed into the sea, broken down into mineral grains, recombined in some other configuration. The rock we eventually find is the survivor. It is not the average. It is the lucky. The continental crust, on average, is much older than the ocean floor. Some of the oldest rocks on Earth are continental, dating back nearly 4 billion years, found in stable cratons that have somehow avoided the deeper recycling for almost the whole of the planet's history. But these old rocks are exceptional. The vast majority of the continental surface is much younger, and the ocean floor itself is geologically young everywhere. Nowhere on the ocean floor is the rock older than about 200 million years. The older the ocean crust, the more likely it has already been swallowed back into the mantle at some subduction trench, melted, and recycled into the slow circulation that drives plate tectonics. What this means in plain terms is that a vast majority of the rock surface that existed 69 million years ago is no longer present at the surface today. It has been buried, deformed, eroded back to mineral grains, or recycled entirely. Only the survivors remain. The survivors are real and informative, but they are only a small sample of what was once there. The fossil record is even more selective than the rock record. Fossils form only under specific conditions. Rapid burial. Low oxygen at the depositional site. The right minerals in the surrounding water to slowly replace the original tissues with stone. A typical organism, even one belonging to a vast and successful species, leaves no fossil at all. Bones and teeth and shells and the woody parts of plants fossilize most readily. Soft tissues almost never do. Skin, organs, feathers, fur, brains, and most of the chemistry of life are recorded only in rare circumstances of exceptional preservation, found in places like fine-grained shales where conditions were unusually still and the burial unusually quick. The dinosaurs ruled the Earth for 160 million years, and we know them from perhaps a few thousand reasonably complete skeletons in total. Spread across millions of square kilometers of rock, whole genera are known from a single tooth or a single fragment of bone. From this it follows, almost as a matter of arithmetic, that the fossil record we have is not a sample of life as it was. It is a sample of the lucky few organisms that died in the right place, at the right time, in the right kind of mud, and survived the long subsequent reworking of the planet's surface. It is fragmentary, biased, and incomplete in ways that careful paleontologists are constantly working to correct, but never able to fully overcome. Most of what has ever lived on this planet has left no physical trace whatsoever. Whole forests have grown and decomposed and left only a faint isotopic ratio in the soil they once stood on. Whole herds of animals have lived and died and left no bone in stone. Tropical environments, the warmest and wettest and most biologically rich, preserve the worst. Decay is fastest, where life is densest. The richest ecosystems leave the faintest records. The cold, dry margins of the world, where life is sparse and slow, often leave better records than the abundant tropics, simply because their conditions slow the processes of erasure. The continents themselves move. Over the timescales we are considering, the position of every landmass has shifted. The Cretaceous Earth was a different planet, mapped differently, with shorelines in different places, mountain ranges in different places, climate zones in different places. The sediments that formed 69 million years ago are now scattered across continents that have drifted to new positions. Some of those sediments are now buried under kilometers of younger rock. Some of them have been lifted into mountain ranges and eroded back down to nothing. Some of them are at the bottom of the sea, sometimes the same sea as before, and sometimes a different one. To find a particular thin band of sediment from 69 million years ago, a geologist has to know exactly where to look, and even then the band may not be exposed, may not be preserved, may not be reachable. Mountain ranges erode at a rate of roughly a few millimeters per year. Given enough time, even the largest range is reduced to a low rolling plain. Given more time, the plain itself becomes sediment and is washed gradually into the sea. The Himalayas, the youngest great range, are still rising, but already the rocks at their summits are being reworked by ice and rain and gravity, sent down in slow rivers, deposited far away as the alluvial plains of South Asia. The Rockies and the Alps are older and lower than they once were, their sharp peaks softened by tens of millions of years of weather. The Appalachians, much older still, are gentle worn folds in the eastern landscape of North America, the eroded remnants of a range that was once as high as any on the planet. Given enough time, every mountain comes back down. Given enough time, every plain becomes sediment again. The planet's surface is in constant slow circulation, and nothing built upon it is permanent, in geological terms, no matter how solid it may appear from inside a single human lifetime. Glaciers, when they advance, scrape continents bare. Ice sheets have repeatedly cleared the northern landmasses down to bedrock in recent geological times. The Canadian Shield, the Scandinavian Shield, the high plains of Siberia, the northern moors of Europe, all bear the marks of the most recent ice age, which ended only about 12,000 years ago. Some of those ice sheets pushed material thousands of kilometers south of where it had originated, depositing it in long ridges and chaotic piles when the ice eventually melted. They will do so again. The glacial cycle is part of the planet's recent rhythm, and it is one of the most efficient erasers of recent geological information that the Earth possesses. The picture that emerges from all of this is one of constant rewriting. The Earth's surface, on the timescales the Silurian thought experiment is asking about, is not a fixed text in stone. It is a slow, restless, constantly edited document in which most of what was ever written has already been overwritten, eroded, buried, or otherwise lost. The world remembers only what conspires to be remembered. The slow, long features the mountain belts, the wide marine basins, the broad isotopic shifts that record changes in the global atmosphere are recorded faithfully. The brief sharp features the events that lasted only a few thousand years, the layers that were only a few centimeters thick, the chemical signatures that depended on a particular configuration of preservation conditions are recorded poorly. They are easy to miss. They are easy to misread. They are easy to lose entirely. And it is the brief, sharp features that a civilization would be. Whatever else our own industrial era may be, it is brief on the planet's timescale. 2.5 centuries. A geological eye blink. A civilization that lasted 10 times as long as ours, 3,000 years in the industrial mode, would still be brief. A civilization that lasted 100 times as long, 25,000 years, would begin to leave a more durable signal, but still a small one against the scale of deep time. The Silurian inquiry, when honestly worked out, comes down to this. The Earth holds the long, slow story of itself well. It holds the brief, sharp events of its own past only when conditions conspire to preserve them. And conditions, more often than not, do not conspire. The world remembers, but selectively, and the things it forgets vastly outweigh the things it keeps. This is the foundation on which everything else in tonight's inquiry rests. The Earth is a restless machine. The Earth is a constant rewriter. The Earth holds only the lucky survivors of its own past. And from here, the question of what an industrial civilization would or would not leave behind takes on its actual shape. We can now ask the harder version of the question. Given the way the Earth's memory actually works, what specifically would a civilization leave that could last the kinds of times we are considering? What could a careful geologist of the deep future actually find? That is the work of the next part of the evening, and it is the heart of the Silurian inquiry itself. Part 4. What would survive of a civilization? Now the question can finally be asked in its proper form. Imagine, for the thought experiment, an industrial civilization on Earth. Suppose it ends 69 million years ago, near the close of the Cretaceous period, just before the asteroid arrives that will end the dinosaurs. Suppose, for the purposes of the inquiry, that this civilization had electricity, vehicles, agriculture, manufactured chemicals, and global trade. Something broadly comparable, in its energy use and its chemical footprint, to a brief slice of our own present moment. It is the late Cretaceous. The continents are arranged differently than they are today. Sea levels are higher. Tropical forests cover most of the warm latitudes. The civilization, whatever it was, exists for some number of centuries or millennia, and then it ends. 69 million years pass. What is left for a later geologist walking across these rocks to find? Most things, the careful answer says, are gone. Cities are gone. Buildings are gone. Roads and bridges and harbors are gone. Concrete, the material on which most modern civilization rests, crumbles into its component minerals within centuries, to a few millennia under ordinary weather. Within a few 100,000 years, no recognizable structure built of concrete would survive at the surface anywhere on Earth. 69 million years is more than 200 times that long. There is nothing left to find. Metal artifacts are gone. Even the most stable structural metals would corrode, oxidize, and disperse into the surrounding sediments over geological time. Iron rusts away in centuries when exposed to ordinary weather. Steel a little longer, but not very much longer. Aluminum oxidizes more slowly, but its surface films break down under continuous weathering. Copper and bronze last longer than iron, but even they corrode away over the timescales we are now considering. Even gold, which does not corrode chemically, would be reworked, scattered, and redistributed by erosion and tectonic activity. The atoms of the gold would still be present somewhere on the planet, redistributed into the slow inventories of the crust. The shape of any object made of those atoms would be entirely gone. Books are gone. Paper is gone. Plastics, despite their modern reputation as eternal, are degraded by sunlight and microbes on timescales of centuries to tens of thousands of years. Most paper does not last a single millennium. Most plastic, in surface conditions, breaks down over a few thousand to a few tens of thousands of years. Fabrics, ropes, organic materials of any kind decay quickly under ordinary atmospheric conditions. None of the obvious physical artifacts of an industrial civilization survive across 69 million years. Not the ones we would think to look for first. Not the ones that occupy our imagination when we picture what is left of a vanished people. The fossils of the civilization's builders themselves are also almost certainly gone. As with the dinosaurs, only a vanishingly small fraction of any population would ever leave a fossil at all. The chance that a fossil of a member of a civilization that lasted only a few thousand years would be both preserved and later discovered is extraordinarily small. The fossil record's selectivity is the great equalizer here. Even successful populous species leave only a thin scatter of remains across the rock, and a brief civilization measured against the long timescales of fossilization would barely register at all. glass, ceramics, bricks, fired pottery. These last longer than metals or plastics, but they still erode and disperse over tens to hundreds of thousands of years at the surface. Buried deeply enough, in just the right conditions, they could persist much longer, but only as individual fragments scattered through a layer of sediment, no longer recognizable as the artifacts of a coherent civilization. They would look, to a careful future geologist, like unusual mineral inclusions in a thin band of sediment. Curious, perhaps, but not in themselves evidence of anything in particular. This is the discouraging half of the inventory. Almost everything we instinctively reach for when we imagine the leftovers of a civilization is gone. The civilization's physical body would not survive deep time in any recognizable form. And yet, this is not the whole story. The thought experiment becomes interesting precisely because there is another half of the inventory. A handful of signals could, in principle, survive across tens of millions of years. Not as artifacts. Not as objects you could pick up. As anomalies in the chemistry of the rocks themselves. As thin shifts in the ratios of elements and isotopes recorded in the sediments, laid down during the civilization's brief existence. These are the markers the Silurian thought experiment focuses on, and they are the markers a careful future geologist would look for if they were already wondering whether something had once happened in a particular thin slice of the planet's deep past. The first of these markers is carbon. A civilization burning vast quantities of fossil fuel releases carbon into the atmosphere with a particular isotopic signature. The carbon in fossil fuels is depleted in the heavier isotope of carbon because the plants that originally became those fuels preferred to take up the lighter isotope during photosynthesis. When that carbon is released, the global ratio of the two isotopes shifts. A short, sharp shift in this ratio, recorded in the sedimentary layers of the world, would be one of the most durable signatures an industrial civilization could leave. It would last as long as the sediments themselves lasted, potentially for tens of millions of years, in places where the relevant sediments survived in readable form. The second marker is nitrogen. Industrial fertilizer production fixes nitrogen from the atmosphere in patterns that the natural nitrogen cycle does not produce, with a different isotopic signature than biologically fixed nitrogen. Once this artificially fixed nitrogen enters the biosphere, it flows through soils and waterways and shallow marine sediments. Spikes of nitrogen with the wrong isotopic ratios for natural processes, recorded in soils and shallow marine deposits, could persist as a faint chemical anomaly across very long times. The signal is small and easily masked by ordinary biological variation, but it is genuinely present in the modern record and would, in principle, be present in the sediments of any sufficiently advanced civilization. The third marker is rare earth metals. The manufacture of electronics depends on rare earth elements concentrated in particular minerals, small exotic metals like neodymium and lanthanum and cerium, ordinarily distributed in extremely low concentrations throughout the crust. Industrial activity reworks these elements, concentrates them in particular places, and eventually disperses them in modified patterns into the soils and sediments of the planet. Anomalous concentrations of these elements in thin layers of sediment in patterns not produced by ordinary weathering could survive as a subtle but recognizable compositional anomaly. The fourth marker, and one of the most distinctive, is plutonium and other long-lived artificial radioisotopes. The detonation of atomic weapons in the mid-20th century and the operation of fission reactors before and since has produced isotopes that do not occur naturally on Earth in any significant quantity. Some of these have very short half-lives and are gone within decades or centuries. Others have half-lives long enough tens of millions of years, in a few cases to leave a faint but measurable trace across the kinds of geological timescales we are considering. The plutonium spike from atmospheric weapons testing in the middle of the 20th century is, even now, a globally recognizable horizon in marine and lake sediments. Some of the longer-lived artificial isotopes from that same era will still be present in detectable quantities when 69 million years have passed. The fifth marker is the chemical residue of plastics. The polymers themselves break down, but some of the chemical compounds they leave behind, unusual halogenated organic molecules, for instance, can persist in fine-grained, oxygen-poor sediments for very long times. These are not the molecules of plastic as we know it. They are the slow degradation products, the long-lived breakdown chemistry, the ghosts of the original materials. They are present in the modern sedimentary record, and they could, in principle, persist as faint chemical traces across geological time. The sixth marker is the pattern of mass extinction itself. A civilization causing a rapid change in global climate and ocean chemistry would leave behind a pattern of extinction in the fossil record, with species disappearing together within a thin band of sediment, and recovery taking hundreds of thousands of years afterward. Such patterns are visible in Earth's past. They are the defining feature of the boundaries between major geological periods, but their causes are well established and natural in all the cases we know. A civilizational extinction would, in principle, have its own particular pattern, distinguishable in subtle ways from a natural mass extinction. The distinction would be difficult to make, however, given the limits of the record. The seventh marker is the broad shape of a brief, sharp climate excursion. A civilization that altered the planet's climate would leave behind a short interval of unusual temperature and chemistry, recorded in the isotopic signatures of deep-sea sediments and polar ice cores. The interval would be brief, in geological terms, and the planet's natural feedbacks would slowly bring the system back to its previous configuration over a much longer period of recovery. Such excursions are present in Earth's past. None of them, when their full chemistry is examined, requires or strongly implies a civilization. All of them are naturally explained. But they show that the broad shape of what an industrial civilization would leave behind is, in principle, the kind of thing the planet's record can preserve. Picture a future geologist of some 140 million years from now, 69 million years, on top of the 69 million years we have already imagined, walking across a thinly exposed cliff face. Slowly they trace a layer of dark sediment a few centimeters thick. Within that band, the chemistry shifts. Carbon ratios change. Nitrogen spikes. Rare metals concentrate. Traces of artificial radioisotopes register on their instruments. The band lasts no longer than the width of 2 fingers. That band, no thicker than a hand, is the entire industrial age. Below it, the long, ordinary quiet of the planet. Above it, the long, ordinary quiet again. The geologist runs their fingers along the layer, taking a sample. They study it for a season. They confer with colleagues. They conclude that something unusual happened here, on a global scale, in a brief window of the planet's past. Whether they go further than that, whether they recognize the layer as the signature of a civilization, depends on questions that the rocks themselves cannot answer. And here is the central, sobering observation of the Silurian thought experiment, held in its quietest form. Even with these markers all present, recognizing them as the trace of a civilization would be extremely difficult. The signatures are subtle. They overlap, in many of their individual features, with naturally occurring events. They are spread across thin, easily missed bands of rock that may not even be exposed in any place we happen to look. To recognize a civilization, the future geologist would need to find several independent signatures converging in the same thin slice of rock in many places around the world, with no plausible natural cause that fits them all together. Such convergence has not been found in Earth's past. The thought experiment is not built on a discovery. It is built on the much quieter observation that, if such a convergence had occurred long enough ago, we very likely would not be able to recognize it. The Earth would hold the layer in some scattered surviving form, and the layer would carry its anomalies, but the planet would not, on its own, tell us what the layer meant. The reading would have to come from us, and the reading would be uncertain. The honest conclusion of the thought experiment, in its careful form, is that almost any industrial civilization, if it lasted only a few centuries to a few thousand years, would be very nearly invisible in the deep geological record. Whether or not anyone was here before us, the Earth would not be in a position to tell us with confidence. This is not a melancholy conclusion. It is a calibrated one. It is the kind of conclusion a careful astrobiologist needs in order to think clearly about what to look for on other worlds. It is the kind of conclusion a careful geologist already accepts in their everyday work as the ordinary limit of what stone preserves. And it is the kind of conclusion that, when held patiently, opens the inquiry into its next phase, into the strange echoes of brief, sharp episodes that the planet's deep past does in fact contain. Part 5. The Earth's brief, sharp episodes. Earth's past does contain a small handful of episodes that, in their broadest outline, resemble the kind of thing an industrial civilization might leave behind. None of them is evidence of one. All of them have natural explanations that fit the data better than any other interpretation. They are worth describing carefully, because they illustrate exactly the kind of signal the Silurian thought experiment is asking about, and exactly why such signals, on their own, do not carry the weight of proof. The clearest example, and the one most often cited in calm scientific discussions of the Silurian hypothesis, is an event that occurred about 56 million years ago. It is known in the literature by a long name, but for tonight's purposes the long name is unnecessary. It is enough to call it a thermal maximum, a brief, sharp episode of global warming that interrupted the otherwise gentle climate of the early Cenozoic. In broad outline, the event went like this. Global temperatures rose by something between 5 and 8 degrees Celsius in a geologically short period of time, a few thousand years at the outside, though the precise timing remains the subject of careful continuing research. The warming was driven by a massive injection of carbon into the atmosphere and oceans. The isotopic signature of the released carbon points to a biological source, organic carbon, or carbon-rich material that had once been organic rather than carbon released directly from volcanic activity. The oceans warmed, acidified, and lost oxygen at depth. There was a major extinction of deep-sea life. On land, ecosystems shifted dramatically as climate zones moved poleward. Many mammal lineages, including the ancestors of many modern groups, expanded into the warmer world and diversified rapidly during the event. The event lasted, from peak warming to full recovery, about 200,000 years. The shape of the event is suggestive. A brief, sharp release of biologically derived carbon, driving rapid warming and rapid biotic change. The general outline is exactly the kind of thing an industrial civilization might, in principle, produce. And yet, when the full chemistry of the event is examined, the additional fingerprints that would point to an industrial source are absent. There is no anomalous nitrogen signature. There are no rare earth concentrations. There are no artificial radioisotopes. there are no chemical traces consistent with plastic-derived compounds. The carbon excursion is present, but it is the only fingerprint present. And the carbon itself, when its precise isotopic chemistry is examined, fits well with a natural source, most likely a destabilization of methane reservoirs beneath the sea floor, possibly triggered by the volcanic activity associated with the opening of the North Atlantic Basin around that time. The event is well understood in its natural form. There is no need to invoke anything else. Nothing in the rest of the chemistry would support such an invocation, and the natural mechanism is sufficient on its own to explain everything that is observed. Several other smaller carbon excursions are recorded in Earth's deeper past. Most are smaller than the Great Thermal Maximum, but they share a similar broad shape. Some occurred in the deep Mesozoic, during the long age of the dinosaurs. Some occurred in the Paleozoic, hundreds of millions of years before the dinosaurs. Some are associated with massive volcanic episodes, long-sustained outpourings of lava and gases that altered the planet's climate over millions of years and triggered major extinction events. Others are associated with rapid sea level changes that affected the storage of organic carbon in shallow marine basins. In each case, the broad outline of a brief, unusual layer with altered isotopic ratios is qualitatively comparable to what an industrial civilization might leave behind. In each case, the additional fingerprints that would point to a non-natural source are missing. The natural explanations are not perfect. There are always remaining puzzles, always remaining details that scientists continue to refine, but they are sufficient to account for the patterns we actually observe. This is the calm, careful version of the question. It is a question about what the planet's record can and cannot reliably say. The existence of brief, unusual layers in Earth's past is not, by itself, evidence of any prior civilization. The Silurian thought experiment is careful to make this point. It is not arguing that any particular event in the geological record is suspicious. It is arguing only that, in principle, the geological record of an industrial civilization would look very much like a brief, unusual layer in the rock, and that such layers are, by the nature of the record, very difficult to interpret with full confidence either way. The argument is calibrational. It is not historical. It is meant to tell us how cautiously to read brief, unusual layers when we find them, not to tell us that any particular such layer is the residue of a hidden past. There is, in addition, a deeper structural point that the Great Thermal Maximum quietly illustrates. The event itself is so well studied, examined in cores from the deep sea, in soil sequences in continental basins, in carbonate chemistry, in the migrations of mammal lineages, in the patterns of land-plant communities, in dozens of different lines of evidence, that the natural explanation for it has had decades of careful refinement. The reason we can confidently attribute the event to natural causes is precisely that we have looked at it from so many different angles, and the full chemistry of the event fits the natural explanation in detail. This is what proper interpretation of a brief, unusual layer looks like. It is multidisciplinary. It is patient. It is built on the convergence of many independent lines of evidence. It is exactly the kind of careful work that, in principle, could reveal a non-natural origin for some other event in the planet's past, if such an origin existed, and that, equally, would be required to rule out a natural origin with confidence. The signal an industrial civilization would leave in the deep record is real but quiet. The natural noise of the planet is much louder. To find a civilization's fingerprint reliably, you would need to find several independent signatures converging in the same thin slice of rock. In many places around the world, with no plausible natural cause that fits them all together. No such convergence has been found in Earth's past. We have looked carefully at the great thermal maximum and the smaller excursions, and each of them has yielded to natural explanation. The thought experiment is not asking us to revise this finding. It is only asking us to notice that the absence of such convergence is partly the absence of a previous civilization and partly the limit of the planet's memory. There is a small comfort in this. If a civilization had been here before us and had lasted long enough to make a difference, we would probably know. We would find the convergence of fingerprints, the multiple lines of evidence aligning in the same layer, the kind of structured anomaly that no single natural process could produce. The fact that we do not find this is, gently, the strongest argument for our being the first. Not a proof, not a certainty, but a reasonable presumption, given the way the record works. The fingerprints simply are not there. The Earth has been examined patiently by many people over many decades, in many places, with many techniques. The brief, sharp episodes of its past have all yielded to natural explanation. There is no convergence pointing to anything else. The most likely interpretation, by a long margin, is that we are the first to do what we are doing on this planet. And yet, that interpretation rests on the limits of the record. It is a probabilistic finding, not a logical proof. The planet might have once held a civilization whose fingerprint was simply too small, or too localized, or too long ago to leave detectable convergence in the surviving rocks. The thought experiment leaves this possibility quietly open, not because there is any positive evidence for it, but because the limits of detection cannot rule it out. The honest summary, then, is that we have no evidence for a prior civilization on Earth, that the brief, sharp episodes of Earth's past are all well explained by natural processes, and that the deeper question of whether any such civilization could have existed at all and remained undetected is one the planet's own record is not in a position to fully answer. This stance, held patiently, is the proper one for the Silurian thought experiment. It is calm. It is non-conspiratorial. It is grounded in the actual properties of the geological record. And it opens the inquiry into its next and largest phase, the phase in which the question is turned outward. Because the same logic that applies to Earth's deep past applies even more strongly to the deep pasts of other planets. And it is in that outward turn that the Silurian thought experiment finds its deepest meaning. Part 6. The question turned outward. The deeper reason the Silurian hypothesis was published, and the reason it continues to matter in scientific conversation, is that it is really about other worlds. The question of what an industrial civilization on Earth would have left behind is a stand-in for a much larger question. What would astronomers see in the light of a distant planet around a distant star if a civilization had once existed there and was now long gone? The Earth is, for these purposes, only the most accessible laboratory. The actual question lives in the chemistry of other skies. When astronomers analyze the atmospheres of planets around other stars, something that they are now beginning to do in serious detail, using the largest telescopes ever built, they look for what are called biosignatures. These are chemical fingerprints in the atmosphere that would be very difficult to explain without life. Oxygen, for instance, is highly reactive. Without something to constantly replenish it, the oxygen in Earth's atmosphere would be gone within geological time, locked away in rust and rock and water. The fact that Earth's atmosphere contains roughly 20% oxygen, sustained against this loss for hundreds of millions of years, is itself a biosignature, the chemical evidence of vast amounts of life producing oxygen faster than the planet can absorb it. A similar argument applies to certain other reactive gases, particularly when they appear in combination. Oxygen alongside methane is a particularly strong fingerprint. Both gases are reactive. Their persistent coexistence is hard to maintain without ongoing biological replenishment. Astronomers have been working for many years now to develop the tools and techniques that will eventually let them detect such combinations in the atmospheres of small rocky planets around nearby stars. Some scientists also look for what are called technosignatures. These are chemical or physical fingerprints that would be hard to explain not only without life, but without technology. Industrial waste gases, for example, are not naturally produced in significant quantities. Certain artificial gases used in refrigeration and electronics are entirely industrial in origin. The detection of such gases in the atmosphere of a distant planet, even in trace amounts, would constitute strong evidence of a technological civilization. Other proposed technosignatures include unusual ratios of isotopes that natural processes do not produce, patterns of artificial light visible on a planet's night side, and, of course, the deliberate broadcasting of radio signals the original target of the long, patient outward survey that has been listening for half a century or more. A technosignature in a planet's atmosphere would be a kind of testimony, not the civilization itself, but the chemical record of its activity. And the Silurian hypothesis asks the natural follow-up question. How long would such a technosignature persist after the civilization that produced it had ended? The answer, when worked out carefully, is unsettling in a quiet way. An industrial civilization that lasted only a few centuries would change a planet's atmosphere noticeably, but only for the span of its existence. Once the civilization ended, the atmosphere would relax back toward its natural state over a few thousand to a few tens of thousands of years. The reactive industrial gases would be broken down by sunlight and by chemical reactions with other atmospheric components. The carbon dioxide spike from fossil fuel burning would slowly be absorbed by the oceans and locked into carbonate sediments. The atmosphere of the planet would, within a geologically short time, return to something close to its pre-civilizational equilibrium. The chemical signatures of the civilization, the unusual gases, the isotopic ratios, the trace metals, would be deposited into the planet's rocks during its existence. These signatures could persist much longer than the atmospheric anomalies, but only as thin layers of altered chemistry within the planet's sedimentary record. And those layers, as we have already established, are difficult to detect even from the planet's own surface. They would be essentially invisible from interstellar distances. The technosignature would be gone from the atmosphere within a few tens of thousands of years. The geological signature would remain in the rocks, but only as evidence accessible to someone walking the planet's surface with the right instruments, not to a distant astronomer reading the planet's atmosphere from across the gulf of space. A civilization that lasted 1,000,000 years would, of course, leave a much stronger signal. The atmospheric chemistry would be sustained at non-equilibrium levels for far longer. The geological record would carry a thicker, more persistent layer of anomalous chemistry. There is reason to wonder, however, whether any technological civilization typically lasts that long. The honest answer is that we do not know. We have only the single example of our own, and it has not yet been here for very long at all. The first proposal of the Silurian thought experiment as a published question was barely a decade ago. The discipline of formally studying technosignatures as a serious astronomical enterprise has only existed for a few decades. The question of how long technological civilizations typically persist is itself an open question, and one that the patient outward survey is in some sense already trying to answer, by listening for the signals that would tell us we are not alone and noticing the silence it has so far returned. The Silurian hypothesis can be read, then, as a quiet warning about how astronomy will need to interpret what it sees. The next generations of telescopes will be able to characterize the atmospheres of many small rocky planets around nearby stars. Some of those atmospheres may carry faint chemical anomalies. The hypothesis suggests that even on a planet that once carried a civilization, the signal at any random moment of observation is very likely to be the signal of the planet itself, the natural background, mostly recovered, with only a faint trace of the civilization's past activity layered into the deeper geology. The atmospheric fingerprint of a civilization is a brief feature on the timescale of planetary chemistry. The geological fingerprint is durable but inaccessible from interstellar distances. This has practical implications for how astronomers will think about the search for life and the search for technology. The most likely successful detection, if any such detection ever comes, will probably involve a civilization that is active at the moment of observation. The lights are on. The atmospheric chemistry is sustained at non-equilibrium levels. The reactive industrial gases are present. The technosignature is fresh. Searching for the residues of civilizations long since gone is, by contrast, very nearly hopeless from across interstellar distances. The signatures are too thin, too brief, too thoroughly recovered by the planet's natural processes. The patient outward survey, as covered in an earlier video on the listening itself, has so far found only the natural universe. The signals from the deep galaxy are the signals of rotating neutron stars, of cold molecular clouds drifting through interstellar space, of ordinary stars going through their ordinary lives. The atmospheres of the small handful of distant planets we have so far been able to study in detail are the atmospheres of natural worlds. The silence is not, in itself, surprising. It is also not, in itself, conclusive. The Silurian thought experiment gently reminds us that absence of evidence in this domain is not evidence of absence. A civilization that ended 1 million years ago on a distant planet would not, from across the gulf of space, look any different from a planet that had never carried one at all. The chemical clock of the atmosphere runs fast, in the way that geological clocks run fast enough to erase a brief civilization within a geologically negligible time, and then to keep the planet looking exactly as it would have looked if the civilization had never existed. This is a kind of cosmic forgetting. It is not the forgetting of an actively malicious erasure. It is the forgetting of natural processes simply continuing, indifferent to what has happened in the past. The atmosphere relaxes. The sediments accumulate. The continents drift. The star burns steadily through its long, mature phase. The planet goes on with its planetary business, and the brief, unusual chemistry of a civilization passes through it like a single short song through a long instrument, leaving only the faintest harmonic trace. The astronomers, in other words, will have to become geologists in their imaginations. They will have to think about what an atmosphere remembers of itself, and over what stretches of time that memory survives. They will have to think about how thin a fingerprint can be, and how easily a brief, sharp episode in a planet's life can pass beneath the threshold of detection from across the void. They will have to learn to read the atmospheres of distant worlds the way Earth's own geologists read its rocks. Patiently, with humility, with full awareness that absence of evidence is not the same as evidence of absence, and with the recognition that the long silence the listening has returned so far may be, in part, the silence of planets that have forgotten what they once held, simply because the planets themselves do not hold such things for very long. This reframe of cosmic silence as cosmic forgetting, rather than cosmic absence, is one of the gentlest implications of the Silurian thought experiment. It does not require us to believe that anyone has been here before us, on Earth or on any other particular world. It only requires us to notice that the universe is older and quieter than we are accustomed to remembering, and that the things which are old and quiet are not always empty. They may simply be at rest. They may simply have completed their brief, sharp chapters and returned to the long, patient, ordinary state that is the actual default of planetary existence. The civilizations that may have once existed in the long history of the galaxy may, for the most part, be present in the universe only as faint chemical traces in worlds whose atmospheres have long since moved on, and whose rocks hold those traces too quietly and too deeply for any signal of them to cross the dark. Part 7. The Long View. So we return to the question with which we began, and we let it rest in its widest form. Are we the universe's first civilization? The honest answer, when held against the long memory of any planet, is that the universe is not in a position to tell us with certainty. The galaxy may have carried many civilizations across its long history. Most of them, if any existed, would by now be present only as faint geological traces in worlds whose surfaces have moved on. The silence we observe, when we listen with the patience of the long outward survey, may in part be the silence of planets that have already forgotten what they once held. This is the gentlest implication of the Silurian thought experiment. The hypothesis is not really a story about hidden ancestors. It is a story about how briefly our presence registers on a planet that does not preserve very much, and how quietly the world goes on remembering only its slow, patient changes. The dinosaurs ruled the Earth for 160 million years, and what we know of them is the residue of an exquisitely small fraction of the lives that passed through that long age. The first cells on this planet existed for 3 billion years, and we know them mostly from chemical traces in the most ancient surviving rocks. The Earth holds the long, slow story of itself faithfully. It holds the brief, sharp episodes only when conditions conspire to preserve them. The brief, sharp episodes are most of what we, in our short attention spans, find dramatic. They are the parts of the story the planet remembers least well. What does this mean for our own moment? Our industrial era is, by any honest reckoning, a brief, sharp episode. 2.5 centuries on a planet 4.5 billion years old is a duration so short that, on the planet's own timescale, it would barely register as more than a single thin band of unusual chemistry, recorded only in the lucky few places where the relevant sediments happen to be deposited and happen to survive. The carbon shift is already in place. The nitrogen anomaly is already in place. The plutonium spike is already in place. The microplastic distribution is already in place. The concentrated metals are already in place. The mass extinction is already underway. The layer that future geologists may someday walk across is already being laid down in the slow, patient way that all such layers are laid down. Whether anyone walks across it, and whether they recognize it for what it was, is a question that depends entirely on what comes next. There is something gentle in this. We are not asked to feel small in any cruel way. We are asked only to notice the actual scale of the planet we are on. The Earth has held many long ages. It has held the age of the first cells, and the age of the early oceans, and the long, stable ages of the deep continents, and the brief, sharp boundaries between them. It has held the age of the trilobites, and the age of the great forests of carboniferous swamps, and the long, deep age of the dinosaurs, and the long, quieter age of the mammals. We are a recent chapter in a story that has been telling itself patiently for billions of years. The planet will continue to tell that story whether or not we are here to listen. The story does not particularly require us, and yet we are here. We are listening. We are looking back across the long sediments of the past, and we are looking forward across the long sediments of the future, and we are trying to understand where, in the great patient story, we have arrived. The Silurian hypothesis is one small part of that effort. It is a calibration exercise. It is a thought experiment about the limits of geological evidence. It is a humbling observation about how quietly the planet remembers brief episodes, including, perhaps, our own. And it is, ultimately, a kind of opening a recognition that the universe is older and stranger and more patient than the foreshortened sense of time we live by ordinarily allows us to see. The wonder it offers is the kind of wonder only deep time can produce. We are small in this kind of inquiry. The planet is old. The signals we leave on it, however large they may feel from inside our own civilization, are small and brief and quiet against the long horizon of geological time. The Patient Outward Survey, as covered in an earlier video on the long story the universe is telling, has shown us that the universe has tens of billions of years of stelliferous time still to run. The galaxy will continue. Many more chapters will be written on this planet and on others. The signals we are laying down now will fade and become part of the long, ordinary background of the planet's surface. The atoms we have rearranged will be rearranged again. The chemistry we have altered will return to equilibrium. The Earth will continue. The galaxy will continue. The slow, quiet, patient business of the universe will continue. And what was, briefly, the noisy chapter of our industrial era will become a thin band in deep sediment, in the places where deep sediment survives at all, and the long memory of the planet will hold it quietly, neither honored nor erased, the way it holds all of its brief, sharp episodes with the same patient indifference that it holds the dinosaurs and the trilobites and the first quiet cells in the warm early seas. This is not a sad observation. It is, if held gently, a peaceful one. The Earth holds us lightly. It does not particularly require us to be remembered, but it does not refuse to remember us either. Whatever we do next, the planet will continue, and the long story will continue with it, and we will be a part of it. A brief, sharp episode, quietly preserved or quietly forgotten, in a record that is patient enough to absorb us either way. If anyone else has ever been here, in the long ages before ours, the Silurian hypothesis tells us, gently, that we may never be in a position to know. The Earth would not preserve the convergence of evidence well enough to settle the question. And if no one else has ever been here, the same hypothesis tells us, with the same gentleness, that we are the first to do this particular thing on this particular planet, and that whatever we leave behind will, in time, settle into the same long, patient memory that holds everything the planet has ever held. Either way, the inquiry closes in calm. The question that began as a provocation, what if we are not the universe's first civilization, turns inward and softens and becomes the much quieter question of what the planet itself remembers and over what stretches of time that memory survives. The answer is a small one. The world holds the long, slow stories well. The brief, sharp ones it holds only when it must, and only where the conditions allow. We are a brief, sharp chapter. Whether anyone, in any deep future, walks across the thin band of our layer and recognizes us for what we were, that is a question that does not need to be answered tonight. Tonight, only the long, patient memory of the planet. Tonight, only the deep time underneath the present moment, holding it gently. Tonight, only the recognition that we are inside a very old story, and that the story does not require us to know how it began, or to know what came before us, or to know what will come after. The story is enough on its own. The patient memory of the Earth is enough on its own. The long, slow, ordinary turning of a small blue planet around a small ordinary star in a long ordinary galaxy is enough on its own. And so we leave the question where it has always rested, not as a mystery to be solved, but as a quiet measure of how briefly we have been here and how patient the planet is. Whatever we leave will be a thin band in deep sediment, in the places where deep sediment survives at all. The Earth will continue. The galaxy will continue. The long story will continue. Let your breathing slow. Let the long quiet settle around you. Sleep well and good night. There is a particular quality of attention that deep time requires, and it is worth lingering with for a moment before we move further into the inquiry. The mind, asked to hold 1 billion years, does not really hold it. It holds a kind of placeholder for the number, a vague gesture toward the vast, and then it slips back to the human scale, almost without noticing. To work with deep time the way working geologists and astrobiologists work with it, you have to keep returning to the actual numbers, gently and patiently, until the numbers begin to settle into something the mind can sit beside without immediately translating it into something smaller. 1 million years. 100 million years. 1 billion years. These are not figures of speech. They are real durations, with real chapters of planetary history filling them, and they are the scales on which the Silurian inquiry actually operates. There is also something quietly steadying about the way the planet itself does this work, simply by being old. The continents we walk on were once arranged differently. The seas we sail across were once in different places, or did not exist at all. The mountains we look up at were once flat, or were once even higher than they are now, or were once at the bottom of a sea that is gone. The Earth's slow rearrangement of itself is the basic background against which every shorter story unfolds. The dinosaurs lived through some of that rearrangement. The first cells lived through far more of it. We are living through it now, although the rates are slow enough that we do not, in ordinary life, perceive any of it directly. The continents move at the speed of a fingernail growing. The mountains rise and fall over tens of millions of years. The ice sheets advance and retreat over tens of thousands. It is worth saying again, plainly, what the actual ages of things are. The Earth is about 4.54 billion years old, with that figure measured by the careful comparison of radioactive isotope ratios in some of the planet's oldest surviving rocks and in the meteorites that formed at the same time as the Earth itself. The oldest individual mineral grains so far identified on this planet are about 4.4 billion years old, small zircon crystals embedded in younger rocks in Western Australia, surviving like tiny ancient seeds through everything that has happened on Earth since they first crystallized. The first robust signs of life are perhaps 3.5 billion years old, recorded as the layered structures of microbial mats preserved in ancient shallow water sediments. The first eukaryotic cells, the cells with internal compartments, the cells that made all later complex life possible, appear in the record about 2 billion years ago. The first multicellular organisms, complex enough to be visible to the unaided eye, appear about 600 million years ago. Land plants colonized the continents about 470 million years ago. The first vertebrates step out of the water about 370 million years ago. The age of dinosaurs begins about 230 million years ago, runs for 160 million years, and ends 66 million years ago in the boundary event we already know. The first true primates appear in the early Cenozoic, perhaps 55 million years ago. The first hominins, the ape lineage that would eventually give rise to humans, appear about 7 million years ago. Our own genus appears about 2.5 million years ago. Our own species appears about 300,000 years ago. Agriculture appears about 12,000 years ago. The industrial era appears about 250 years ago. Listening to these numbers in series, one after another, is a useful exercise. Each one is a real duration. Each one is the length of a chapter of the planet's own story. The numbers grow gentler as we approach the present, smaller and smaller, until the most recent few are vanishingly brief compared with the long, deep stretches that came before. And it is in the contrast between those long, deep stretches and our own brief recent moment that the Silurian inquiry finds its actual texture. We are not lost in the middle of a long story. We are at the very thin recent end of it. Almost everything that has ever happened on this planet happened before we arrived. Almost everything that will happen on this planet will happen after we are gone. The planet's long memory holds the long, deep middle of the story with patient care, and holds the thin recent end of it only because the thin recent end is still being written. There is one more piece of context worth adding before we turn the corner into the heart of the inquiry. The galaxy itself is older than the Earth. The Milky Way has been here for something like 13 billion years, with stars forming and dying in it across that entire span. Many generations of stars have come and gone since the galaxy began. The Sun is only the latest of those generations, a third or fourth generation star, formed from material that had already been processed by earlier stars and seeded into interstellar space by their deaths. The chemistry that makes up the Earth and that makes up us was forged inside stars that lived and died long before the Sun was born. When we look up at the night sky and see the long band of the Milky Way, we are looking out through a structure that has been here in something like its current form for an enormous fraction of the age of the universe itself. This matters for the Silurian inquiry because it sets the stage on which the larger question, the question of whether anyone else has ever existed in the long history of the galaxy, is asked. The galaxy has been here long enough for many civilizations to have risen and fallen, in principle, before our own. Whether any of them did, we do not know. The Silurian thought experiment, when turned outward, becomes a meditation on what we could and could not detect of any such past civilizations, whether they were on this planet or on others. And the answer, as we will see, has a certain symmetry to it. The Earth would not easily preserve the trace of a previous civilization on its own surface. And the galaxy, when looked at across interstellar distances, would not easily preserve the trace of a previous civilization on any of its worlds. The fading of evidence is a general feature of long timescales, not a peculiar feature of this particular planet. We are walking, in this inquiry, toward a recognition that is both calibrational and contemplative. Calibrational, because it tells us how to read the chemistry of distant planets and the chemistry of our own deep past with appropriate humility. Contemplative, because it leaves us with the quiet observation that the universe is older than us, that planets are older than us, that brief civilizations are brief on the timescales of planetary memory, and that the long, patient story of the universe goes on regardless. The Silurian thought experiment is the doorway through which both of these recognitions enter. We are still in the early chambers of the doorway. There is more to walk through yet. Let us also linger on a small but important distinction that the literature is careful about, because it is the kind of distinction that separates the careful version of the inquiry from the more excited versions that sometimes try to claim its name. The Silurian hypothesis is not the claim that something definitely existed before us and has been hidden from view. The Silurian hypothesis is the question of what would and would not survive across deep time, framed as a thought experiment specifically to support careful detectability research. These are different kinds of claims, and the difference matters. The first kind of claim that something definitely existed and has been hidden is a historical claim. It would require positive evidence to support it. It would require artifacts, or chemical convergence, or some other concrete signal pointing to a non-natural origin for some specific feature of the geological record. No such evidence exists. The careful scientific consensus is that there is no positive case to be made for a previous industrial civilization on Earth. The published Silurian hypothesis does not attempt to make that case. The authors explicitly state, repeatedly, that they do not believe such a civilization existed. The second kind of claim that we could not, in principle, detect such a civilization if it had existed is a methodological claim. It does not require positive evidence about any particular event. It requires careful reasoning about the properties of the geological record and the limits of inference from that record. The published Silurian hypothesis is essentially an exercise in this kind of reasoning. It is an effort to think clearly about what the planet preserves, what it loses, and what kinds of fingerprints would and would not survive across geological time. The reason this distinction matters is that the second kind of claim is much weaker than the first, but also much more informative. The first kind of claim would, if true, overturn a great deal of what we think we know about Earth's history and would have enormous practical implications. The second kind of claim, by contrast, is mostly a refinement of our understanding of the geological record itself. It tells us how cautious to be in our interpretations. It tells us what kinds of signals to look for. It tells us how confident to be in our reading of the planet's own past. It does not require us to revise any historical claim, but it gently revises the certainty with which we should hold our historical claims. This is the kind of work that careful science often does. It does not overturn the consensus. It refines the consensus. It clarifies what the consensus is actually saying and what it is not saying. It draws sharper boundaries around the limits of what we know, so that we can be more honest about what lies inside those limits and what lies outside them. The Silurian hypothesis, read as this kind of refinement, is a genuinely valuable piece of methodological work. It does not unsettle our picture of Earth's past in any substantive way. It only sharpens our understanding of the limits of that picture. The same is true, in an even more important way, of the hypothesis when it is turned outward. The methodological refinement applies even more strongly when we are looking at the deep pasts of other planets. We have only ever had one planet to study geologically, this one. The patterns of evidence we are calibrated to recognize are the patterns we have learned to recognize from our own world. When we extend our reasoning to other planets, where the geological record may be even harder to read, the methodological refinements of the Silurian inquiry become more important, not less. The same caution applies. The same humility applies. The same recognition that brief, sharp episodes are easily lost applies. And the implication is the same, only more so. If we cannot easily distinguish the trace of a civilization from the trace of a natural event on our own planet, where we can sample the rocks directly and study them with every available technique, we will have an even harder time making that distinction on a planet many light years away, where we can study only the integrated chemistry of the upper atmosphere at the moment of observation. This is why the published Silurian hypothesis was framed as an astrobiology paper rather than as a geological one. The authors were not primarily interested in Earth. They were primarily interested in what their reasoning implied for the search for life and technology elsewhere in the galaxy. And what it implies is sobering. The signals we would expect to find of a long-gone civilization on a distant world at any given moment of observation are likely to be very small. They are likely to be confined to thin layers of unusual chemistry in the planet's rocks, which we cannot see from interstellar distances. The atmospheric signals will have relaxed back toward equilibrium within a geologically brief time after the civilization ended. The most reliably detectable kind of distant civilization is one that is currently active in the present moment. The harder, fainter, more easily missed kind of detection is the one that would correspond to a civilization that has come and gone, and whose only remaining trace is in the geology of its planet. This sobering observation has consequences for how we think about the silence we have so far observed in the long outward survey. If most civilizations are brief, and most brief civilizations leave only weak atmospheric signals at the moment of observation, then the absence of detected signals from the galaxy as a whole tells us less than we might at first think. It tells us, primarily, that we have not yet detected any currently active civilizations of the kind we would expect to be able to detect at interstellar distances. It does not tell us very much about whether there have been past civilizations or whether there are future ones still to come. The galaxy is a long story. It has been telling itself for many billions of years. The fraction of that story we have so far been able to listen to in the patient outward survey is small. The Silurian hypothesis quietly reminds us that the silence we have heard so far may also be, in part, the silence of planets that have completed their own brief, sharp chapters and returned to the long, ordinary quiet that is the actual default of planetary chemistry. There is a humility in this that is worth sitting with. The universe is older than us. The galaxy is older than us. The planets that orbit the galaxy's stars have, on average, been there for billions of years. Many of them have, in principle, had time enough for civilizations to rise and fall multiple times over. We do not know that any have. We do not know that none have. The patient outward survey continues, and the brief, sharp chapters of any planet, including ours, pass beneath the threshold of detection across the long ages. This is the texture of the question, when it is held with care. It is not a sharp question with a sharp answer. It is a quiet question with a quiet answer, and the quiet answer is mostly about the limits of what we can know, given the way the universe arranges its memory. There is a storyteller's economy in the way the Silurian hypothesis sets up its question. The authors choose Earth as the stage because Earth is what we know. They choose the deep past as the timescale because the deep past illustrates the relevant limits most clearly. And they choose an industrial civilization as the imagined subject because the industrial era is the only example of a technological civilization we have available, namely, our own, and it is therefore the only one for which we can do the necessary detectability calculations with reasonable confidence. The choice of subject is not a claim about what kind of civilization actually existed. It is a choice of laboratory specimen. The thought experiment uses what is available to study what is general. This is the mark of careful scientific reasoning, clarity about which features of the example are essential to the argument, and which features are merely the contingent details of the example chosen. The Silurian hypothesis is clear about this. The contingent details are 69 million years ago, on Earth in the late Cretaceous. The essential features are deep time, the limits of the geological record, and the fading of any brief, sharp signal against the patient natural background of planetary memory. So we hold the inquiry steady. We do not let it slip into excited claims of hidden histories. We do not let it slip into anxious claims of widespread cosmic ruin. We hold it where it actually sits, in the careful middle ground of methodological refinement, where it tells us, quietly, that the universe is older and stranger and more patient than our ordinary picture of it allows, and that the limits of what we can know about the deep past of any planet are tighter than we tend to assume. From that careful middle ground, the rest of the inquiry can proceed. One further texture is worth adding to the picture before we move further into the inquiry, because it bears directly on how the chemistry of an industrial civilization actually finds its way into the planet's long memory. The atmosphere, the oceans, and the sediments of a planet are not three separate systems. They are one slow, coupled system, with material constantly moving between them. Carbon released into the atmosphere is, over time, absorbed into the oceans. Carbon in the oceans is, over time, incorporated into the shells of marine organisms or the slow accumulation of organic matter on the sea floor. Carbon on the sea floor is, over time, buried beneath younger sediment and incorporated into the rock record. The journey from atmosphere to rock takes time, typically thousands to tens of thousands of years for the first stage, then much longer for the deeper burial. But the journey happens. The atmosphere does not hold a brief, sharp anomaly forever. The oceans buffer it. The sediments record it. The rocks preserve some fraction of it, in the slow, patient way that all geological records are made. The same is broadly true for other elements. Nitrogen released into the air settles into soils and waters. Heavy metals released into surface environments make their way into sediments. Radioisotopes deposited from the atmosphere into rainfall make their way into soil profiles and into the upper layers of marine and lake mud. The chemical fingerprint of any brief, sharp episode is therefore distributed across the whole surface system of the planet, with each layer of that system carrying a slightly different version of the signal. The atmosphere carries the freshest, most easily distorted version. The oceans carry a slower, smoothed version. The sediments carry the most durable version, but only after the chemistry has been mixed and modified by the journey from air to sea to mud to rock. What this means in practice is that the durable record of a brief, sharp episode is the sedimentary record, and that the sedimentary record carries a smoothed, slightly altered version of the original chemistry. The signal is real, but it has been processed. The isotopic ratios are still there, but they are the ratios that ended up in the rock, not the ratios that were originally in the air. The trace metals are still there, but they have been redistributed by the slow circulation of the oceans before they were finally deposited. The artificial radioisotopes are still there, but only as the slow, steady accumulation into the upper sediments over the brief few decades during which they were released. For a careful future geologist, the convergence of multiple smoothed signals in the same thin band of sediment is exactly the signature they would be looking for. Not the raw atmospheric chemistry of the moment, which is long gone. Not the surface artifacts of the civilization, which are also long gone. The smoothed, integrated chemistry recorded in the sediments themselves, with multiple independent fingerprints converging in the same layer. This is what would carry the recognizable signature, if anything would. And it is the kind of pattern that would require careful, multidisciplinary analysis to recognize as the trace of a civilization, distinguishable from the kinds of natural events that can produce some, but not all, of the same fingerprints. This is why the published Silurian thought experiment focuses so heavily on the question of convergence. A single anomaly is rarely diagnostic. A carbon shift on its own could be many things. A nitrogen spike on its own could be many things. A rare metal concentration on its own could be many things. It is only when multiple anomalies show up together, in the same thin layer of sediment, in the same patterns across multiple sites around the world, that the case for a non-natural origin becomes strong. And convergence is, by its nature, harder to recognize than any single signal. It requires that all the relevant analyses have been done. It requires that the analyses have been done in the same places. It requires that the analyses have been done with techniques sensitive enough to pick up the relevant fingerprints. And it requires that someone has gone looking for the convergence in the first place. None of these requirements is trivial, even in our own present-day study of our own planet. They are even less trivial when projected onto the geological record of a planet many light years away. This carefulness about convergence is one of the reasons the Silurian hypothesis remains a thought experiment rather than a definitive answer. The thought experiment frames the question, identifies the kinds of signals that would matter, and notes that the convergence of those signals would be necessary to make the case. It does not assert that such convergence does or does not exist somewhere in Earth's past. It only asserts that, if it does not exist in the data we have so far examined, that absence is partly evidence about the past and partly evidence about the limits of our examination. The honest scientific position is calibrated by both. So as we move toward the next stretch of the inquiry, hold this carefulness in mind. The signals we are about to discuss, the carbon shifts and the nitrogen anomalies and the rare metals and the radioisotopes, are not the kinds of signals that can be read from a single line of evidence. They are the kinds of signals that have to be read together, across multiple lines of evidence, across multiple sites, with multiple techniques. And the recognition of any particular pattern as the trace of a civilization, rather than the trace of some natural event, depends entirely on whether the convergence of multiple independent fingerprints can be established. We are walking, in other words, into the most carefully reasoned part of the inquiry. The next stretches of the inquiry are about what the planet actually does and does not preserve, and about how those preservations and erasures shape the question. They are about the limits of memory itself, the limits of detection, the limits of inference. And they are, in their quietest form, about the patience required to hold the question well, without claiming too much, without dismissing too quickly, without letting the inquiry slip into excited speculation or anxious certainty. The Silurian hypothesis, at its best, is a model of this kind of patience. We can practice it, here, together, for the remainder of the long evening ahead. Picture a long, flat coastal plain, somewhere on a Cretaceous continent, 69 million years ago. The sky is hotter and wetter than the sky over most of the modern world. The vegetation is dense and tropical. The river that runs across the plain carries sediment slowly from a low range of hills in the interior, depositing layer after layer of fine mud and sand into the slow water of the estuary where the river meets the sea. The mud accumulates slowly, a millimeter a year perhaps. Some years, the river floods and lays down a thicker layer in a single season. Some years, the river is too low to deposit anything significant, and the surface of the plain dries out for a while before the next wet season brings new sediment. Now imagine that, within this long, ordinary cycle of deposition, something brief and unusual happens. The chemistry of the air shifts. The carbon isotope ratios change. The nitrogen flux through the plain increases. Trace metals from somewhere far away, somewhere on this continent or on another one, begin to wash through the river system, and into the estuary. The change is recorded in the mud as a faint shift in the chemistry of the layer being deposited at that moment. The change lasts for some number of centuries, perhaps a few thousand years. Then it ends. The chemistry returns to its previous values. The mud continues to accumulate, year after year, layer after layer, with the brief, unusual interval recorded as a thin horizon of altered chemistry, a few centimeters thick, embedded within a much thicker accumulation of normal sediment. 69 million years pass. The estuary that was here in the Cretaceous is gone, of course. The continents have moved. The seas have risen and fallen many times. The land that was the coastal plain has been buried under younger sediments or lifted up into a low range of eroded hills, or partly removed by glacial activity in some more recent ice age. The thin band of altered chemistry, if it survives at all, is somewhere now perhaps exposed on a cliff face along a present-day river that has cut down through younger rocks, perhaps buried at depth beneath a city that has been built on much younger sediment, perhaps lifted up to the side of a mountain ridge where it can be reached only by careful climbing. Most of the original estuary's sediments are gone. The lucky few that survive are scattered, hard to find, and often hard to recognize even when they are found. A geologist walks the cliff face. They notice a band of dark sediment, a few centimeters thick. They take a sample. They send it to a laboratory for analysis. The laboratory reports that the band carries unusual carbon isotope ratios, with a brief, sharp shift toward the lighter isotope. The geologist notes this. They have seen such shifts before. They are common enough in the deep record to be recognized as a general feature of brief, sharp episodes, though their interpretation requires care. The geologist asks the laboratory to look more closely. The laboratory finds, in addition to the carbon shift, an unusual nitrogen anomaly in the same layer, with isotopic ratios that do not match the natural patterns of biological nitrogen fixation. The geologist notes this with more interest. Such combined anomalies are less common, though not unknown. The geologist asks for further analysis. The laboratory reports trace metal concentrations in the same band that are several times higher than the regional background. The geologist now has 3 independent anomalies in the same thin layer, and the convergence is starting to feel unusual. They go back to the cliff. They look for the same band in other sites along the same stratigraphic horizon. They find it, in fragmentary form, in several other locations across the continent. The same combined chemistry is present. The convergence is robust. The natural explanations begin, slowly, to feel less sufficient. At this point, the geologist faces a choice. They can continue to assume that some natural process they have not yet identified is responsible for the combined anomalies. They can frame the layer as a new kind of natural event, worth further study, but not requiring any radical reinterpretation. Or they can entertain the possibility that the combined chemistry points to something that was not natural to a brief episode in the planet's past, during which something other than the ordinary geological processes was active. The Silurian thought experiment is, in part, an effort to help geologists think clearly about how they would make that choice and how confidently they could make it. In the actual current state of the science, no such convergence has been found in Earth's deep past. The brief, sharp episodes that exist in the record carry 1 or 2 of the relevant fingerprints, but not the full convergence of multiple independent fingerprints that would distinguish a civilizational signal from a natural one. The Great Thermal Maximum carries a clear carbon shift, but no nitrogen anomaly, no rare metal anomaly, no artificial radioisotopes. The various smaller, ancient carbon excursions carry similar partial patterns, with the carbon shift but not the additional fingerprints that would suggest a non-natural origin. The natural explanations are, in each case, sufficient. The convergence that the thought experiment identifies as the threshold for confident detection has simply not been observed. This is, again, an empirical finding rather than a logical proof. The convergence might exist in some part of the record we have not yet examined carefully. The convergence might exist in some part of the record that has been eroded away. The convergence might exist in some part of the record that we have examined, but with techniques not sensitive enough to detect it. The honest scientific position is to acknowledge all of these possibilities, while noting that, on the evidence currently available, the most likely interpretation is that no industrial civilization existed on Earth in the deep past. The Silurian hypothesis adds to this position a quiet methodological refinement. Even if such a civilization had existed, the convergence of detectable signals might not have survived the planet's long erasures, and so the absence of convergence cannot be read as conclusive proof of absence. This is the heart of the inquiry. This is the still center around which everything else turns. The Earth holds its long, slow stories well, and its brief, sharp episodes poorly. The brief, sharp episodes that do survive are, with very few exceptions, naturally explained. The faint possibility that some brief, sharp episode might have had a non-natural origin and yet failed to leave the convergence of fingerprints that would let us recognize it as such. This faint possibility is what the Silurian thought experiment quietly preserves. It does not insist on the possibility. It does not deny it. It holds it in the careful middle ground, where careful science prefers to hold such things, until and unless evidence emerges that would tip the balance one way or the other. And so we move on, carrying this careful middle ground with us. The inquiry has many more chambers to walk through, but the center is now established. From here, the rest of the evening can unfold at the gentle pace that the topic deserves. It is worth pausing once more, before the final stretches of the inquiry, to consider what kind of civilization the thought experiment is actually imagining. The word industrial does a lot of work in this conversation, and it is not always clear exactly what is meant by it. The most useful working definition, for the purposes of detectability, is a civilization that produces enough chemical and energetic disturbance to leave a measurable global fingerprint in the planet's surface environments. This is a relatively high bar. It implies a civilization that has scaled beyond the local. It implies a civilization that has begun to alter the planet's atmospheric chemistry, the planet's distribution of trace metals, the planet's nitrogen cycle, or some other planetary scale system. It implies, more or less, a civilization that has begun to do at planetary scale the kinds of things our own industrial era has been doing for the past 2.5 centuries. A civilization that remained local, even one with great technological sophistication, but confined to a single region or a single small portion of the planet, would leave a much weaker geological signal than the kind of civilization the thought experiment is imagining. The fingerprints would be limited to a small geographic area. The atmospheric chemistry would not be globally altered. The trace metal distributions would not show up in marine and lake sediments around the world. The artificial radioisotopes, if any, would be confined to local soils rather than being deposited globally by atmospheric circulation. Such a civilization, in geological terms, would be very nearly invisible across deep time. The published Silurian hypothesis is therefore implicitly considering the more visible kind of civilization, the kind that operates at planetary scale, because only that kind can be expected to leave a fingerprint that even our most patient geology might in principle recover. This is, in some sense, a comforting observation. Any civilization that has not yet scaled to planetary impact is unlikely to leave a deep geological signal, regardless of its technological sophistication. The Silurian inquiry is therefore not about all civilizations that might ever have existed on Earth. It is specifically about civilizations that would have left planetary-scale fingerprints. The fact that we find no such fingerprints in Earth's deep past is therefore consistent with several possible interpretations. There was no previous civilization at all, or there was one but it did not scale to planetary impact, or there was one that did scale to planetary impact, but its fingerprints have been erased or smoothed beyond our current ability to detect them. The thought experiment makes all of these possibilities visible, without claiming any of them as the correct answer. There is also a temporal dimension that deserves attention. The thought experiment imagines a civilization existing in the deep past, ending well before the present, with the geological record then being read from a great temporal distance. The interesting case for the question of detectability is precisely this kind of long-gone civilization. A currently active civilization on a distant planet would be relatively easy to detect, in principle, if we could observe its atmospheric chemistry at the moment of its activity. A long-gone civilization is the harder case. And the long-gone case is, in many ways, the more likely case statistically. If civilizations are typically brief on geological timescales, then most civilizations that have ever existed in the long history of any planet are, at any given moment, in the past rather than in the present. The patient outward survey is therefore listening, in some statistical sense, for the minority of cases in which a civilization happens to be active right now. The majority of cases, if there are any, are the cases the patient survey is least equipped to detect. This statistical observation gives the silence of the galaxy a slightly different texture. The silence is not the silence of an empty universe, necessarily. It may be the silence of a universe in which civilizations are typically brief, and in which most of them are at any given moment in the past, rather than in the present, with only their faint geological residues remaining to be detected, and those residues being, by the thought experiment's own analysis, very difficult to detect from interstellar distances. The galaxy could, in principle, have carried many civilizations across its long history, with most of them now present only as faint chemical traces in the rocks of worlds that have themselves moved on. The silence we observe would not contradict this picture. It would be consistent with it. This is, again, not a definitive interpretation. It is one possible reading among several. The galaxy might, alternatively, have been very quiet across most of its history, with civilizations being extremely rare. Or civilizations might be common, but most of them might be brief and currently dormant or extinct. Or civilizations might be common and long-lived, but somehow not yet detectable by our particular search techniques. The Silurian thought experiment does not adjudicate between these readings. It only widens the space of plausible readings by reminding us that brief, sharp episodes leave faint and easily erased fingerprints, and that the absence of detected signals is consistent with many possible underlying states of affairs. Holding all of these possibilities open, without insisting on any one of them, is the right way to receive the thought experiment. The calm of the inquiry, when held this way, is the calm of someone who has accepted that certain questions do not yet have answers, and who has learned to be patient with the unanswered space. This is a different kind of calm than the calm of certainty. It is the calm of holding a question gently, without forcing it. It is the calm of waiting, in the long timescales of patient science, for the universe itself to reveal what it can. And it is the kind of calm that a sleep-friendly inquiry of this kind is, perhaps, most able to offer. We have walked through a great deal tonight. We have moved from the foreshortened sense of time that ordinary life requires us to carry, down into the actual scale of Earth's long history. We have walked from there, through the careful statement of the Silurian thought experiment, into the patient analysis of what the Earth's record can and cannot preserve. We have examined the brief, sharp episodes that the planet's deep past contains, and we have seen how they fall just short of the convergence of fingerprints that would let us recognize them as anything other than natural events. We have turned the question outward, toward other planets and other skies, and we have seen how the same logic applies more strongly there. And we have arrived, gently, at the recognition that the question is not, in its deepest form, a historical question at all. It is a question about the limits of memory, the patience of planets, and the brief, sharp chapters in which civilizations, including ours, may pass through the long, ordinary quiet of the universe. The closing reflection has already begun. We do not need to rush it. Let the patient memory of the Earth hold the inquiry now, as it holds everything else. Let the long, slow turning of this small blue planet around its small, ordinary star hold the question of whether anyone has ever done this before, and the question of whether anyone ever will again. The Earth does not particularly require us to know. The galaxy does not particularly require us to know. The long story is enough on its own. The patient memory of the world is enough on its own. We can let the question rest, gently, in the space the inquiry has opened for it. One last small note before we cross fully into the closing reflection, because it gathers the rest of the inquiry into a single quiet recognition. The whole long line of reasoning we have walked together tonight comes down, in its center, to a single observation about scale. We are very small in time. Our entire civilization is brief. The planet we live on is old and patient, and is in no particular hurry to remember us. The galaxy is older still. The universe is older still beyond that. The inquiry that began as a question about whether anyone else might have done this before us turns out, when held patiently, to be a question about how briefly any chapter of the planet's long story can register on the planet's long record, and about how gently the long record holds the brief, sharp episodes that pass through it. We are one such episode. Whether others have come before us or will come after us, the long record will hold all of them with the same patient indifference. The recognition of that indifference, when received as gentleness rather than as cruelty, is the quiet gift the Silurian thought experiment leaves us with. The universe does not require us to be remembered. The universe does not refuse us either. The patient memory of the world is what it is, and we are inside it, and that is enough.